Okay, so you have a question in this, right? Activity question 1.
Yes.
So what do you think should be the approach? Do you have any initial ideas?
I mean, one of this lectures said it is 3k minus 1. So what does that relate to something else? Because
That is the 3k minus 1 is the number of parameters of the GMM, but what we are asking here is how many new parameters are introduced by this inequality that we are using. We are referring to the lambda I case here.
okay.
So lambda I case, there will be 100. There are 100 points. For each point, there will be k lambda values. So lambda ik will be 5 into 100.
Okay. So this is a different set of parameters than 3k minus 1.
Yeah, that's why the question is stating that how many new parameters are introduced, right? So these are like a new set of parameters that you need to, for the EM algorithm to work, you need these many new parameters.
Okay, sir.
Okay.
Yeah.
So yeah, so what we'll do is EM we'll discuss. I'll get started with the collabs, and the collab on EM is, I hope, will, and when we start working through the collab on EM, we will also hopefully understand the EM in greater detail.
Yeah. Sounds good. Yeah. Sure.
Okay, so what we have is uh, first part. First part is going to be looking at the following things. We'll create more space. Yeah. I've just started running the collab, so it's taking some time. Okay. So I hope all of you know what sampling is, right? So sampling is nothing but generating a set of points from some distribution. So sampling is important for us, especially in this week, given that we are studying different types of probability distributions as models and seeing how we can estimate parameters from a set of samples, right? So in NumPy, the way we sample points from a distribution is using what is called a random number generator, right? So that is RNG. We don't need to know what exactly or how random numbers are generated. Typically, they are called pseudo random numbers because they are not really random. It appears random, but they are, once you know something called the seed value, the exact sequence of numbers that will be generated will be fixed, right? So I'll just demonstrate this. For example, here we are drawing some 10 integers in the range 0 to 2. So 2 is not included in the range. So we are just drawing integers which could be either 0 or 1. We are drawing 10 such integers. So if you notice the sequence, it is 1, 1, 1, 0, 1, something, right? Now, no matter how many times I run it, it will be the same sequence. Okay, but the moment I remove the seed value, what happens is every time I run it, I'm going to get a different sequence. So for example, here it's 0, 1, 0, 1, something. Now if I run it again, it is 1, 1, 0, 1, and so on. Another time it will be something else, right? So in general, what we try to do in machine learning, and especially if you are writing papers or even otherwise, it's important to fix a seed value. It could be anything. could be 1001 or whatever, right? Any number of your choice. But the nice thing in fixing a seed value is that all the numbers that you generate can be reproduced, right? So if you close your laptop today and then run it 10 days later, the sequence of random numbers that you see will remain the same. Okay, so this is important for your either research or whatever you're working on, because numbers simply keep changing. You won't know on what set of data you got your results, right? So that is why we have introduced this whole random number generator. Right, so now that is set, we'll start with maximum likelihood estimation, right? So we have some data set X here. So these are going to be zeros and ones, as I already mentioned. Now we need to find the MLE of this parameter P, right? If you use a Bernoulli distribution, then we need to find the maximum likelihood estimate of the mean using this data set, right? So what is that? What do you think that value is going to be?
Mean.
It's the mean, right? So that's as simple as that. So what we'll do is we just say x dot mean and run this cell, right? So, and that's all, right? So because you could go write a loop, say for I in range of x dot shape of 0, just number of points in the whole thing, and then you could say some value equal to value plus x of I, and then finally divide the mean is equal to value divided by x dot shape of 0, right? This is what I've done, right? So print value, you will see that it's the same thing. Okay, so not the same thing. Why am I getting y0? Six instead of 0.506. Okay, just a second. Sorry, it's not value, it's mean, right? So I hope all of you got it, right? So instead of doing all this loopy business, we are just saying that the maximum likelihood estimate is the mean. So is there anyone who didn't get this part, what we are trying to do here? I hope all of you got it. So just give me 1 second. I just need to change some indentation settings. Okay. All right. So once you understand that, now we are, instead of generating just 1000 data points, we are going to generate, I think, yeah, so sorry, this was, yeah, I just spent some time on this itself. So what kind of a coin is this? By looking at the maximum likelihood estimate, what can you say?
Unbiased?
Yeah, it is an unbiased coin, right? So 0.506, of course, it's, if you just take the estimate, then it is, you could say it's biased because it is not exactly 0.5. But what this does, what RNG.integers is doing is that it is generating either 0 or 1 uniformly at random, right? So this is generating integers uniformly at random, meaning there are only 2 integers it's generating, then the probability for each of them is 0.5, 0.5, right? So it is kind of confirmed when we try to do this. It's pretty close to 0.5. Okay, but now we don't want just unbiased coins. We also, since we are dealing with Bernoulli distributions, we must also be capable of generating or sampling coins from a bias, sorry, sampling points from a biased coin, right? So here the bias is 0.8. Always the parameter P we associated with 0.8. which is the probability of x equal to 1, right? So now this is a biased coin. Okay, so if you look at the 20 observations here, you'll see that they are predominantly 1, right? So most of them are 1, which is a reflection of this bias. Okay, did everyone get this part? What we are trying to do here?
So can you explain the last one, part point to point?
One?
Yeah, that one, yes.
Yeah, so all right, yeah, this is a different function or different method. Maybe I didn't mention that. So what we are doing here is choice is a method in, again, this random number generation library. Okay, so in that library, choice, what it does is whatever list you give it, it will pick one number from it. It will pick either 0 or 1, and depending on the probabilities of these numbers, the probability of picking 1 will depend on this number point. So what we are essentially saying is that this function is going to pick either 0 or 1, but it is going to pick 0 with a probability of 0.2, and it is going to pick 0.8, 1 with a probability of 0.8. That is what this is doing. So for example, if I pick 1,000 samples or so 1,000 data points from this Bernoulli distribution, then let us count how many ones are there, right? So if I just sum x, that will be the total number of ones. Do you agree? The
Oh,
data will,
yeah.
right? So if I now divide by 1,000, I will see. So you see that it's 0.815. Okay, so it's close to 1.
Okay. Yeah. So means if we have choice like 3, 0, 1, 2, then we have to enter in P also 3 probabilities, right?
Exactly, yeah. So
Yeah.
P also you'll have to make it
Yeah.
3.
Okay. Yeah. Thank you.
Okay, so we'll go to this. We'll come there also. So we'll come to that also. So this problem, what it's asking us to do is get 1,000 points from a Bernoulli distribution with p equal to 0.7. And once you do that, compute the MLE of p for this sample. Okay, so this note is important here. So see, when do you do MLE? When does it make sense to do maximum likelihood estimation?
When we have a unknown parameter or distribution.
So when we have a model with us and some data, and we don't know what the parameters are supposed to be, right?
Yeah, right.
So, but here we are saying that p is already 0.7. Okay, so one valid question that we all should ask is, you already know the parameter p, then why are you computing the maximum likelihood estimate? Right? So this is the note. This is what the note says, right? So the reason we do it is one important reason is to verify if whatever we are learning is the right thing, right? And the best way is to do it with simple data sets like this. Okay, so the MLE should be close to 0.7 in this case, and this kind of an exercise helps us verify that nicely. Okay, so now can someone tell me how to generate 1,000 points from a Bernoulli distribution with this probability?
So we have to use that choice function and 0, 1, then size equals to 1000.
Okay, size equal to
0.3,
1,000.
0.7, right?
0.3, 0.7.
Okay.
For p equals.
All right. So this is going to be the data set. Okay, let's run this. And we'll just look at the first few, right? First 5, just to get an idea of how it looks. Here there's nothing to look, it's just ones and zeros. Now MLE for maximum likelihood estimate will be what?
Mean.
Nothing, right? So let's do that. X dot mean. What is the mean we get? 0.707, right? Pretty close to 0.7. Now, what do you think will happen if I change this to say 10? You think you will get 0.7, close to 0.7, or will it be even more close to 0.7, or what do you think will change?
It will be away from 0.7.
Okay, let's try that. Yeah, in fact, it is 0.3, right? So it's so away from 0.7 that it's almost embarrassingly bad, right? So that shows us the importance of the sample size, right? When we are estimating parameters like P or whatever, through whatever method, be it MLE or Bayesian modeling, whatever, the number of samples in your data point is very important, right? You should have a decent number of samples to ensure that you get a good enough estimation of your parameter. So the more the data points, better is your estimate. You have 10,000 data points, then this is again closer. That was 0.707. This is 0.697. You use 100,000 data points, it gets better and better, right? But at some point, it's also going to reach its own limit, right? So there's only so much we can do through these numerical methods. There'll always be some error in estimation. Okay, so that is problem 2. Now, just to see what we have, we can visually understand this using a bar graph, right? And so if you're looking at Colab for the first time and you don't know some function, one way is to just type the function and wait for some time. This kind of a help will be generated, right? So sometimes this works, but if it doesn't work, then this question mark will always work. Okay, so if you type the method and enter a question mark, what you will get is what the function is or method is, what are the arguments, what are the parameters, and so on, right? So if you look at the parameters for a bar graph, what we have as x, the first parameter is the x coordinates of the bars. Okay, so what will be the x coordinates for us? What are the 2 bars that we want to plot? For a Bernoulli
Parameter and sample size.
right. So we want to plot 2 things, 2 bars, right? The 2 bars should correspond to number of zeros and number of ones. Okay, and this should be count of zeros and this should be count of ones. This is the height. So the height of the bars, right? So that is the second parameter. First parameter is where on the x-axis these bars should lie. So they should be at 0 and 1. And then the height should be the number of zeros and number of ones. Okay, so how do we count the number of zeros here? X is the data set. So you tell me how to do the count part.
Length of x minus x dot sum.
Okay, that is correct. That is good. So we'll do count once first. First, you have given this as x dot sum. So this will be x dot sum will be the number of ones, and count zeros will be, as you said, length of x is correct. Like, so in NumPy, it's like usually we do everything using shapes, right? So x is of shape 1000, right? So 1000 minus count once. Now if we plot this, we get a bar graph, right? So centered at 0 and 1, and there are 300 points, 300 samples or other observations which belong to 0 and 700 which belong to 1, right? Roughly. So this is just to get you used to plotting graphs in Matplotlib. Okay, any doubts here? Who we did the plotting? Okay. Right. So the next problem is a slight extension of this. We are asking you to study the impact of the size of the data set on the parameter generator. Right? So for each value of n, you will draw one sample, and for each sample, or by sample I mean a set of observations, right? So for each sample you have to compute the MLE, and you must find out how far the MLE is from the true parameter. Okay, so let's go ahead and do this. So what we are asking here is for n in 10, 100,000, 10,000, 100,000, and 1 million. For each of these values of n, first generate n data points from your Bernoulli distribution, which you do as RNG dot choice of 0, 1, with size equal to, what will be the size?
N.
N, and what will be P here?
0.8.2.
0.8.2, right? So this is our data set. This is X. So once you have this X in place, you can generate your PML as I'm using this terminology. PML is again X dot mean, right? So the maximal likelihood estimate for Bernoulli. Now the distance from the true mean, which is 0.2, and the estimate is absolute value of what? PML minus P. Let me write P here as 0.2. Okay, so far I think it's clear. If not, please stop me. Okay, so what I'm doing is these are all Y values, so I'm going to store these values in a list and append these to a list Y. Right? And the X values okay, X and Y may be confusing. So let me say Y axis. Let me call this Y axis. And in the X axis, what numbers will you have? What are you plot? What are you plotting? So
DN versus
N.
n, right? So I'll append n in the x-axis. Okay, so what are we supposed to do now? We are supposed to plot these two. Let's try a simple line plot. Actually, the line plot may not be the right thing. You just need to do x-axis, y-axis. Let's see what we get. Okay, so this is in millions, right? This is 1 million, and notice what happens. The distance is initially very high, so it's something like 0.1, right? In probabilistic, in terms of probabilities, this is bad, right? So a distance of 0.1 between the original and the estimate is pretty high here, but as the number of as n increases, notice that it comes down and it's very low here. Okay, so did you all get the rationale behind this whole thing? It's just a small demonstration of the impact of the size on the ML estimate. there are no questions. If not, I'll move. There are, I'll stop. If not, I'll move on. Okay. So now what we are expected to do is slightly different question now. So we need to sample 1000 points from a biased die, right? So this is like we have to roll a die and roll it 1000 times and see what values we get. Okay, but because the die is biased, the probability of each phase is not going to be 1 by 6. It's going to be these values given here. Okay, so how will you do that? Using whatever we have learned so far.
Will it be choices? Choices.
Yeah, so we'll again go for choice.
1, 2, 3,
What
4,
will be
5,
the
6.
values here?
Yeah.
Okay, 1, 2, 3, 4, 5, 6. I'm going to choose from these.
1000,
How many?
0.1,
1000. And what will be the p-value?
Those 1.2, 0.3.
Okay, so just those values there. P 0.05, 0.05. Okay, so this is what my data set is going to be. Let's just see first 10 points or so, right, of this data set. Okay, so already you can see that there are quite a few 4s being thrown out because 1, 2, 3, 4, right? This 3 and 4 are like having probability 0.3, right? So if you look at top 50 examples, you'll notice that there are 4s and there are also quite a few 3s, right? And as we keep sampling more and more points, this will become better, right? The estimate will become better. Okay, so now what is going to be the maximum likelihood estimate for P3, which is for phase 3? How do you do that? Any answers? Intuitively, what do you think will be a good guess for the third phase?
Sample proportion of
Okay.
the number of
Sample
phases.
proportion, right? So that seems like a good guess. So we'll go with that. We need to find. So what we need to find is find number of times 3 occurs in this data set, right? So this is our task. How many times does 3 occur? And divide that by total number of observations, which is 1000. Okay, so we can do this via the usual for loop, but NumPy has a nice facility. I'll just show you what that is. So let's say x double equal to 3 and simply run it. What will happen is it'll give me an array of the same size as x. Okay, but instead of having the numbers or the observations, it will have a Boolean value true or false. Now it is true if in that index 3 is present. It is false if 3 is not present in that particular index. Okay, so do you get what x double equal to 3 does? It gives you back an array of the same shape as x, but the nice thing is instead of giving you the numbers in x, it's giving you if 3 is present in that position or not. Okay, so once I have an array like this, how can I find the number of times 3 has occurred? Any answers?
If it would have been 0 or 1, then I could have just summed it. But
Okay, so that's a good point. So now I'll if I write this expression, what do you think I'll get as answer?
True.
You see what you get as answer?
it considers true as well. Then you can
Yeah.
directly sum that.
Right. So that is the important point, right? So true is considered as 1. So you can do arithmetic using 2. For example, I can say 12 into true plus minus 5 into true, right? So it is just going to be 12 minus 5. Okay, so it treats true as that 1 and false as 0. So that is something unique to Python. Okay, so now if you look at it, I have an array of true and false. All that I need to do to find the number of times 3 occurs is just sum this array, right? I just use a bracket here, and then if I do this, that will give me number of 3s. And I know that I have 1000 data points. So this will be my estimate for number of for this parameter P3. Okay, so it's kind of close to 0.3 as expected. Okay, did everyone get this part? What we did here?
Yeah.
Okay, so right. So now we'll go ahead and see what this graph looks like. Okay, so again the same bar graph. Now our bars in the x-axis will be the faces of the die, right? So 1, 2, 3, 4, 5, 6, and what we need here is the counts, right? What we did here was number of 3s. Now we need to do this for all 6 faces. Okay, so how do we do this? We can go ahead and do some kind of a loop here. So let's say counts is the list of counts for all the 6 faces. Okay, so I'm going to go over each phase. So for phase in 1, 2, 3, 4, 5, 6, these are the 6 phases. I'm going to ask this question: in what all places is x double equal to phase? Right? Remember earlier this was x double equal to 3. Now it is x double equal to phase. If I sum this, that will be my count for that particular phase. Correct?
Yes.
Right? So all that I need to do now is I need to append this count to my list. And once that is done, I have all my ingredients ready for a bar graph. Okay, so this syntax is incorrect. Okay, so now let's just verify that this is correct. We had 0.1, 0.2, 0.3, so that is expected. Less, then more, then more. 4 is also 0.3, but there is some variation, so it's not exactly 0.3. The last two are very low, 0.05, 0.05, and that is also kind of seen here, right? So these are the two lowest bars, but almost equal in height, right? So if we run this for, let's say, 100,000 times, okay, 100,000, then what will happen? We'll get probably a little more accurate answers, right? So this is 5,000 out of 100,000, and this is 10,000 out of 100,000, 0.1 here. This is 0.2, 0.3, 0.3, 0.05, 0.05. Okay, so that is problem 6. Any questions so far? Okay. So now we move to the Gaussian, and
This is available in later for our reference, right? This
yeah.
because YouTube is not running.
Yeah. This is available. Yeah. Okay. So what we have is compute the density of the 0.5 with respect to this distribution, right? So this will be helpful for your theory assignment also. So please pay attention for this part at least. If you have a Gaussian with mu sigma square, okay, sigma, and you give it a point x to find the density. So you know the formula, right? 1 by root 2 pi sigma e power minus x minus mu whole square by 2 sigma square. That's the formula. So it's a very useful exercise to code this up, because one thing it does is it helps you verify if your numerical answers are correct by plugging it back into this function, right? So explicitly writing this down will help a lot. What I'm going to do now is I'm going to write the formula here as well, and then we'll convert it into pi, right? So this is square root of 2 pi sigma. Okay, 1 by root 2 pi sigma, that is one part. Then we have the other part, which is LaTeX, in case some of you are wondering what this is. I'm opening and closing the brackets, and within I'm going to write x minus mu whole square. Okay, there should be a minus sign, and you divide that by, what do you divide it by? X minus mu whole square by 2 sigma square. Okay, so this is what we are going to write here as a Python function. There are of course methods which directly give you this value, but I think it's useful to do this. So I'll call this, whatever is there in the exponent, the right side part, I'll call this the numerator. Numerator is the following. I am doing exponent e power something, right? So the something is what? Minus x minus u square, okay, divided by, so this whole thing goes, let me add a bracket so that it's clearer. So minus of x minus mu whole square divided by 2 into sigma square. Okay, so that is the numerator. Denominator is just square root of 2 pi sigma, which is np dot sqrt, that will give you the square root of 2 into, there is np dot pi for pi, right? So it's a very direct translation, into sigma. Okay, so that is numerator, this is denominator. All that we need to do is we need to do numerator by denominator. Okay, so that is the Gaussian density evaluated at x for mu comma sigma. So now if you want to find the density of the 0.5, you pass mu, which is 3. So since sigma square is 1.5 square, sigma is just 1.5. And then the point at which you want to evaluate is 5. Okay, so did you get the Python translation? A simple Python function, but it will be very handy later on. Okay, I hope you all got this. All right, so once you understand what a Gaussian is, the density of a Gaussian is. Now we can sample from a Gaussian, right? How do we do that? So a NumPy provides what is called normal for normal distribution. So you can specify the mean. Mean is 3, and the standard deviation you specify 1.5, and you give the number of points, right? The number of points will be 1000. So it's as simple as that. So we have now sampled from a Gaussian. Let's look at, say, the first 5 values and see what we have, right? So roughly they are in and around 3, right? Which is what we want. 3 is the mean. Okay, so we have Gaussian. Now what is the MLE for this case? Is it
Sample mean.
again the sample mean, right? So I again just do x dot mean. Okay, so this is close to 3 as usual, right? As we expect. So that is as simple as that. Now, how do we plot this distribution and see what happens? So instead of doing a bar graph here, it's more appropriate to do a histogram because we are dealing with continuous data, right? So again, we have what is called a plt.hist method, right? Use a question mark that will give you what you need to do. So you just give the data x. Okay, x is the, you go down to parameters, you will see that x is simply the array or sequence of data, and bins is the number of bins that should be there, right? So it will become clear in a moment what the bins are. So I'm just going to go ahead and do plt of x comma. In fact, I just do plt of x, plt.hist of x. Okay. So you get some number of something that looks like a Gaussian. So let's explicitly make this 10 bins. Okay, so in fact, the default seems to be 10. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you could go for higher number of bins also. It's up to you. You'll get something which is more ragged looking. So maybe 10 is a better bin size. And if you want to see the edges of the bins, then you have something called edge color. If you set edge color equal to black, then you will clearly see the outlines of the bins. Okay, so this extra parameter we add so that the contours of the bins become visible. Okay, so is this okay for all of you, or how we plotted a histogram? Okay.
Yes, sir.
Okay, right. So one way to, if you're using collab and if you want to suppress these outputs, you don't want them to keep coming. One thing you can do is use a semicolon after the last line. That will suppress these extra things so that only the plot is visible. Okay, so that's a hack that you can. Okay, now beta distribution. This is the final problem in this particular collab. So visualizing the beta for different values of alpha and beta, right? So again, let me take this opportunity to write the beta distribution here. So beta has 2 parameters, alpha and beta. Okay, focus on the right. If you're interested in LaTeX, focus on the left. Okay, so anyway, so if you have beta of alpha comma beta, what is it? It is e to the power alpha minus 1 into 1 minus p power beta minus 1 Okay, and then you normalize the whole thing by some z, right? Just so that it sums to a probability distribution. Okay, so that is your beta distribution. And now what we are asked to do is plot different values of different distributions for alpha and beta, right? So alpha equal to 5, beta equal to 5. Let's take that case. And we won't worry about the z value right now because that's just a constant and it doesn't really matter. So we'll just plot this term, which is, you can just directly write this in NumPy. So let me position it like this. So p power alpha minus 1 okay, into 1 minus p power beta minus 1. Okay, so this is what I need to plot against some values for p. So what is the support for this distribution? Do you remember what support is? Do you remember what support is from stats 2 days?
0, 1, 0 to 1.
Right. So the support is 0 to 1, right? So that is where the distribution is active for us. So we need to, so in NumPy, if you want to plot something, then you need to specify the values on the x-axis and the values on the y-axis, right? So what we have specified here is the values on the y-axis. So we need values on the x-axis, which is what p should be. So for that, there is a nice way to do it. There is a command called linspace, right? There's a command called linspace. If you provide a range, say in this case, the range is 0 to 1. If you ask it to generate 100 points, it will generate those points for you. So I just demonstrate this first. So I'm just running this, okay? I'm running this and you'll notice that it starts from 0, then it's 0 0.01, 0 0.02, all the way up to 1. So there are 100 points, equally spaced points. That's the important thing. So np.linspace, what it does is it generates these many points between these two endpoints, which are equally spaced. So let's take a smaller value, let's say something like 9 or no, 11. 11 is easier to understand. Okay, so between 0 and 1, now there are going to be these 11 points, right? So which are equally spaced, right? So you get the, I hope you get the idea. If you try length of p, it is 11. So we managed to get 11 equally spaced points between 0 and 1, endpoints inclusive. Okay? Both endpoints are included. Right. So I hope linspace is clear to all of you. Okay, so once you have that, you have all the ingredients to plot the distribution. So I just call this beta dist. So plt.plot p comma p is the x-axis and beta distribution is the y-axis. Let's see what we get. Okay, so this is kind of expected because alpha and beta are equal. Okay, alpha and beta are equal, so it's bang in the center. If you look at the maximum value, it is at 0.5. Okay, so now let's change this to alpha equal to 5 and beta equal to 1.5. What do you think will happen? Where will this peak shift? Will it shift to the left or will it shift to the right?
Right.
Okay, let's try it. Okay, that's correct. Shifts to the right. Now, what about the other way? It will shift to the left. Right. So this, you can use this to verify or visualize different kinds of beta distribution. 0.5 is interesting if you look at it. is this shape. If you remember in the lectures, professor would have mentioned that something like this is for the case where, so what prior is this encoding? You want to look at this as beta of 0.5 comma 0.5 is the prior of some parameter p. How will you express this prior?
0 and 1 are not included actually.
Sorry,
0 and 1 are not included. Both are not there.
you're saying that's the prior?
Excluding 0 and 1.
Okay.
P will take values close to 0, either close to 0 or close to 1. Not
Yeah, that is right. So that is right. So P will take values either very small values or very high values. Of course, in the context of 0 to 1, it is close to 0 or close to 1, but not anywhere in between. So this is the prior that we are trying to encode. Okay. So a few of these beta distributions you are expected to know. Right. So that is the end of the first part of week 4. And in 2 minutes, we'll start with GMMs and EM. Okay, so let's continue with the GMM part.
Hello, sir.
Yeah.
Sir, I had a doubt in that beta functions graph.
Okay.
Sir, my doubt is that when exactly does the graph shift towards left or right, like along the x-axis?
Along the x-axis, right? So see, there is one formula that you can use for the beta distribution. There is a mode value that is given by this. So alpha minus 1 divided by alpha plus beta minus 2, right? This is the mode. I hope you understand, right? The location of the maximum. This is true when alpha and beta are both greater than 1. Okay, so if you look at alpha equal to 5 and beta equal to 1.5, or if you change these values, swap these values, whatever be the alpha and beta, if you compute the mode, you will see where it shifts. Right? So for alpha equal to beta, let's first compute the mode and see what happens when alpha is equal to beta. Mode, what happens? Let's say this is, it could be any alpha minus 1 by 2 alpha minus 1, right? This is the mode for when alpha is equal. How can I rewrite 2 alpha minus 2?
We can take the two common.
Right? So this is nothing but half. Right? So the mode is half when alpha and beta are equal. Of course, all this is for the case where they are greater than 1, right? It's not for less than 1 case. For less than 1, you saw what happened, right? When alpha and beta are 0.5, the maximums, the curve was looking very different. So let's not worry about that. Let's worry only about this case where there is a very clear peak. So that peak will be at the center between 0 and 1 when alpha and beta are equal. Now when alpha becomes greater than beta, then it will shift to one side. When alpha is less than beta, it will shift to the other side. Right? So that's a good exercise. Let's ask this question. Let me ask this question. If alpha greater than beta, then automatically can we show that the mode is greater than or less than 0.5? So how do we do that? So let's take this expression. Take this expression of alpha minus 1. Okay, let me call this mode a better name, or a more, we call it M. Okay, so if I do some algebra, what do I get? M into alpha plus beta minus 2 equal to alpha minus 1, right? Okay, so somehow I need to make use of the fact that alpha is greater than beta. So can someone who is in front of a pen and paper, if you have, can you see how we can, simplify this expression? Okay.
Can we write multiple of beta? Alpha has a multiple of beta.
Yeah, that is one idea. Or let us rewrite it this way. Let me write it as alpha minus 1 and beta minus 1. Okay, it's the same thing. So this is what. So now M is what? I'll just rewritten the denominator. So M is alpha minus 1 by alpha minus 1 plus beta minus 1. So now if alpha greater than beta, then what can I say about alpha minus 1? That will be greater than beta minus 1. Do you all agree?
Yeah, yes, sir.
Okay, so this quantity is then of the form, M is of the form, some see x by x plus y kind of form, where okay, so let me not complicate. So if this is true, if alpha greater than beta, then the numerator is greater than one part of the denominator. So okay, let's now do little more. So I can do the following, right? Alpha minus 1 plus beta minus 1 is greater than what? Or it's less than what? What can I say? Can I replace this with 2 times alpha minus 1? Do you see why this is true?
Yes, yes, yes.
right? So I can do this. Now, consequence, right? What I can do is I can do alpha minus 1 by this whole thing. Is greater than, you see why this is true? See, if alpha greater than beta, then alpha minus 1 is greater than beta minus 1. Then, and what I've essentially done is I've just added the same thing to both sides. Alpha minus 1 plus alpha minus 1 is greater than what? Alpha minus 1 plus beta minus 1, right? This is what I have written down in the next slide. So alpha minus 1 plus beta minus 1 is less than 2 times alpha minus 1. That's what I've written. Now, if you take the reciprocal, since they are all positive quantities, the sign of the inequality will shift. So it will become 1 by 2. 1 by 2 times alpha minus 1. Then you just multiply both sides by alpha minus 1 to get this. So what we have concluded is if alpha is greater than beta, then the peak will be, peak I call the mode, will be this is what we seem to have concluded. So is that convincing enough, or do you all see any problem with this?
Yeah, no, sir.
Okay, right. So I think this is what we got in the part 1 of the collab also, right? If alpha was 5 and beta was 0.5, this, sorry, beta was 1.5 or something like that. This is what we got, right? So it was equal to the right. Okay, anyway, right. So let's go back to EM GMMs. Okay, so what do we do here? So in GMM, what typically we do is we first pick a mixture, one of the K mixtures, and then we sample from that K mixture, right? So we have 3 mixtures here with probabilities 0.3, 0.5, 0.2, and we call them pi 0, pi 1, pi 2 because it's easier in programming to zero index things. So we need to sample one of these 3 mixture. We have to choose a mixture. So how do we choose a mixture in NumPy? We have followed closely so far. How will I choose a point from, sorry, how will I choose a K value with these probabilities?
Choice function.
Okay, that is correct. So I'll again go for my choice function, and what will I choose now?
Values of K, which 1, 2, 3.
1, 2, 3, right? So, but because we are zero indexing, let me just make it 0, 1, 2. Okay, we are only choosing one value right now. So that size will be 1. Now probabilities for these 3 mixtures will be
0.3, 0.5, and 0.2.
That's correct. So who is answering? Thanks. At least someone is answering.
Satyaranjan.
Okay, thanks. Okay. So that I know that the meeting is still on. So the K value I get is 1. So it comes as an array. So I'll just say the 0th element so that it's just a number. Okay, so K equal to 1. So we ended up choosing, in this case, mixture 1. It's not necessary that it should always be mixture 1. It so happens that it is 1. if you use a different seed, for example, use a different seed value, maybe it gives us a different value of 1, right? So let's keep changing the seed value until we get here. So if you use a seed value of 3001, it gives you by 2 mixture 2, right? So this is important even in your k-means context, right? So if you remember the S code that was generated in k-means plus plus, right? This is again something very similar to that. So we have three data points with these probabilities. Then how do you sample one from them, right? So there was this confusion, right? Will always mixture 1 come up? Not necessary. Mixture 1 has the highest probability of coming up, but the other two are also likely, but with lower probabilities. Okay, so in GMMs, once you choose a mixture, what should you do next? You have to sample a point from that particular mixture, right? So here again, that is going to be quite simple. So you sample a normal distribution with in -4. That's mixture 2, right? So 0. What mixture did we get? 1. Sorry. So you'll have to keep going back and forth between the notation. So 1, 0, 1, is equal to 1, right? I'm just sampling 1 point. Okay, so this is the point that I get. Now I'm moving on. Okay, so this is where the real challenging parts begin, right? So you have to, what we did was just sample 1 point from a GM, which is first pick a mixture and then sample a point from that corresponding Gaussian. Now you have to do this for 100,000 points. Okay, so what's a good way to approach this problem?
It could be first generate an array of 100,000 points, and then loop over that and
Right.
get
Yeah, right. So that is what we are going to do. So instead we do the whole thing in a loop for I in range of 100,000. Right. So can please change. I'm kind of used to this 4 indents, so that's why I'm spending time on this. I don't have this, it's kind of disturbing. Sorry for the delay, I need to set this to 4. Yeah, it should work. Okay, so to begin with, what I do is I create space for these 100,000 points. So I'm going to do what is called np.zeros of 100,000, meaning generate an array of 100,000 elements, all of which are zeros. Okay, so once I do this, now I can now do the first step of my GMM. First step of GMM is choosing a value of k, right? So how did we do that? We did it this way, right? So I'll just copy that code. This is how we did it. So choose from 0, 1 or 2 mixtures, one of these 3 mixtures with these probabilities, okay? And then RNG.normal, I'm going to write this now and we'll see what this is actually. Mu of k, sigma of k, Okay, so what I mean by mu of k is the mean of the kth mixture, sigma of k is the standard deviation of the kth mixture. So let me just initialize these values here. Okay, so what are the means? -4, 0, and 5. So I'm going to add them here. They are -4, 0, and 5 for the three mixtures. The variances are 2, 1, and 3. Okay. Now I'll also write the pi values. The pi values are 0.3, 0.5, and 0.2. Correct? So I'll just replace this with pi just to make it generic. Okay. Let me also introduce one variable, which is the number of data points. We call this 100,000. Okay, so this will be n. All these things will become n. This is actually n. Is it clear so far what we have done? Any confusions, doubts?
In the last sentence, instead of sigma var, so
Right.
I
Yeah.
mean, you have declared it var.
Yeah. So I just one thing I need to verify, which is do we pass this variation or the variance, or scale is what? Scale is, so location is the mean, scale is the standard deviation, right? So we have to pass the standard deviation. So that is square root of variance, right? So we should do variance of k np dot square root of, that will be the standard deviation, right? So what have we done so far? We have, this is just our random number generator. We have mu, which is the mean of the three mixtures, var, which is the variance of the three mixtures, pi, which is the pi k value, right? Probability of picking these three mixtures in the first place. N is the number of data points. X is the n data points that we'll have to generate. Initially, they're all 0 to begin with. And first step, we have chosen randomly one of these three mixtures based on the mixture probabilities pi. And once the mixture is chosen, we are generating a random number from the kth mixture, whose mean is mu of k, variance is var of k. Okay, so I hope this is clear. If I run this, I will get, it will take some time because we are sampling. I think we need to sample 100,000 points, right? So now it's done. Once we plot this, it may become slightly clearer what we have done. Okay, with 100 bins, I'm going to plot a histogram of all these points. Okay, so do you see what has happened? We had three mixtures which were centered at -4, 0, and 5, right? So -4, roughly this is -4, this is 0, this is 5. Okay, and because, so why do you think this height is so high for this, lesser for this, and even lesser for this? What is the reason for that?
The pi is 0.5.
Pi's, right? So the pi's are responsible for it. What were the pi's? The center one was 0.5, left was 0.3, right was 0.2. So that is the reason this is having the maximum height, the 0.5 guy. 0.3 is lesser than that, but still higher than what is the third mixture, which is 0.2. Okay, so that is how a GMM is generated. So rather not generated, that is how we generate points from a GMM. So first step, I just elaborate here. Choose a mixture. Second step, sample a point from this mixture, which in our case happens to be a Gaussian. Right? We are only talking about Gaussian mixture models. Okay, so far I think there are no questions. I will proceed.
So how do you know we have three mixtures based on the probabilities?
No, I specify that there are three mixtures. I start with three mixtures. We don't know, so I am not, so what we need to understand that here I am generating the data. So I have control over K, but when you are given a data set, you won't know how many mixtures to choose. Right? So that is typically not known. One thing you could do is you could, look at the data, and if the data is tri-modal, having three modes, then you could, say that it should have three mixtures. Okay, but in general, you will not really know how many we chose. All right, so that is GMM. Now, again, I'll just repeat this point. Here we know what mu, sigma, and pi are. Okay, so you use the EM algorithm only when you don't know these. But why are we doing all this? So that we can verify if our understanding of EM is correct. Okay, so we'll run the EM algorithm on this data set X and see if our means are at least close to what we have here, our estimates, basically.
So this way you can convert any kind of distribution to a multiple normal distribution like this. Like say it's a Poisson distribution, left or right skewed, and then we can just divide it into multiple normal distributions like this. Is that possible, right?
I am not exactly sure. I will have to refer some material and get back. I'm not sure on that.
Okay.
Okay, so EM, what we'll do is we'll break it down into 5 steps. Okay, the actual algorithm is there. Actual algorithm has one E step, one M step, and before that one initialization. Okay, so let me quickly write that down in this tab. So EM has to begin with one initialization is done using k-means, but here we won't be doing k-means. We use k-means with k equal to capital K, the number of mixtures. Okay, so you do the initialization, and then until convergence, you do 2 steps, right? You do the E step, and then you do the M step. Okay, what is the E step? E step is basically following, which is, so initialization will be what? You have some parameters to begin with. So this is theta naught. This is what initialization will give you. Okay, initialization will give you some parameters. So again, what is theta? Theta is this trio of all the mu's, all the sigma squares, and pi. Okay, so how many of these values are there? There will be k mu's, k sigma squares, and k pi's, right? Of course, all the k pi's are not free parameters. Only k minus 1 of them are free, because if you sum the pi k's, they should be 1. That is how we got the result 3k minus. So this is like 3k parameters in total, and just to qualify it, there are 3k minus 1 free parameters, because this is going to be 1. Okay, I hope this is clear. So where will k be? K will go from k equal to 1 to what will be the upper bound?
K.
K, right? Capital K. So always remember that when we say theta, what we essentially mean is these 3k parameters. Okay, mu, sigma square, and pi. So this is the start of EM. To initialize and get hold of one theta naught until convergence. How do you define convergence? Basically, what you're saying is the distance between the theta of so t and theta of, let's say, previous iteration, right? It's less than some, or rather, it's greater than, right? It's not less than. It's okay. So anti-convergence means while the distance between my current estimate and previous estimate is greater than some threshold, means keep going on, right? Continue doing the computations, because I want my values to be very close to each other. Only then I want to stop. Currently, the parameters are not close to each other. They exceed some minimum cutoff defined by me, which is epsilon. Okay, so until this is greater than epsilon, keep going. So what will your E-step do? Your E-step will take the values of lambda ik. And where will it get these values? So let me not write it as lambda ik. Let me write it as lambda time step t plus 1. Okay, it will get this from the theta values. The theta values at time step t. Okay, let me know if you are following this. So that is what the E-step does. So use the current estimate of theta t to get me and give me the next estimate of lambda t plus 1. What is your M step going to do? Going to give you the values of theta t plus 1 and from what? From lambda t plus 1. Okay, so that's what we are supposed to do. Okay, so initialization, we won't do k-means now, but this is how it's generally done. E step is use the theta or t values, get the lambda values. M step is use the lambda values, get the theta values. Okay, so we are now breaking this down into these 5 steps. We begin with initialization. So here what we'll do is, rather than do the k-means, we'll initialize this kind of simply. We'll just give these initial values. I'll write one function in it. What I'll do is, I'll make it 1, 2, 3 as given here. And variances, I will make them 1 each. And pi's are, to begin with, I don't know, right, what they'll be. So I'll just assume that they're all equally probable. So it is 1 by 3, 1 by 3, 1 by 3. It's okay for everyone what initialization we are using.
Yes.
Okay, so one small thing is that we have one convention that we are going to follow now, which is theta naught. What we are going to do is we are going to kind of club these things together in one vector. So rather than writing it as, so why did we use theta in the algorithm's description? Because we wanted some variable to refer to all the 6 parameters, right? So 3k, k is not 6, 9 parameters, right? K is 3 here. So So we have 3 into 3 equal to 9 parameters here, right? So that is important to know. So theta will be these 9 set of 9 values. What I'll do is first 3 values I will reserve it for the means. Next 3 I will reserve it for the variances, and the last 3 will go for the pies. Okay, so rather than have it this way, I just comment these because these are also important. I will generate one theta naught and return that. Right. So now this theta naught contains all the information required for the initial theta naught values. Right. All the information is contained here. I hope this is clear. First 3 refer to means, next 3 to variances, last 3 to the pi values. Okay, once that's done, next step is the E step. Okay, E step can be tricky. So what is E step? We have to get hold of the lambdas from the pi's, from the thetas. Okay, so we very quickly write that here, and that will help us code. What is the E step? So E step is I need to estimate lambda ik. What is that? That is nothing but in terms of probability. What is the probability that the ith data point goes to the kth cluster? So this is what lambda ik is, right? So what is the probability that xi goes to cluster k? Okay, so this is in. So what rule do we make use of here? If you want p of z given x, then what do you do?
Probability of xi given zi.
Right. So we just do the base rule. So this is we first pick cluster k, and then find the density of xi given cluster k. Okay, that is the numerator of the base rule. So p of x, so p of z into p of x given z by p of x, right? So this will be p of not p but f of xi, right? Because we are talking about densities. Okay, I hope this is clear. So now let's just work with this. So lambda ki will be what? It will be this p of zi equal to k. What can I replace that with? What is p of zi equal to k?
Pi
Okay.
of the cluster. Pi of the cluster.
Pi. That is correct, right? So this is just pi k. So f is the Gaussian. So I need the Gaussian. So that I have already computed from an earlier function, right? So this I have with me. Very easy to compute programmatically. Numerically, it's tough. You do it by hand. By f of xi. So f of xi, let me separately write f of xi. What is f of xi going to be?
Sum of all the probabilities of the cluster.
Right? That's correct. Sum of, I'll just use index L equal to 1 to capital K. What I did in the numerator is just for kth cluster. Now I need to do it for all clusters, because the point xi could have come from any cluster. So I do pi L p of zi equal to L equal to 1 to capital K. Okay, so now I can go ahead and replace this here, and so that this looks a little less messy. What I will do is I will just move this fellow here. Okay, this is the formula for lambda ik that we need to compute. Okay, this is the probability that point I belongs to cluster K. Okay, so
Sir,
yeah,
sir, I tried this code, and so my code is running, but answer is not right.
okay,
Sir.
we'll see, right? So let's see why that happens. For now, let's continue quickly so that we need to finish each step, M step, convergence, all these things. So what do we do here? We remember we need to compute the Gaussian. So Gaussian is I just copied from the previous column, right? We already did that. I'm just going to reuse that. This is needed for me. And now the E step, right? E step requires what all? Should return it needs the theta and x, right? So let's take x and let's take theta. So what is mu? You want to extract the means from theta. What are they? Is it the first k, next k, or last k?
Set is for 0, 3rd, and 6th position.
Okay, right. So what is this? This is actually k, right? If you want to generally write this, then there are theta has 3k parameters. So theta's shape is 3k, right? So it has 3k parameters, and I divided it by 3 to get the number of mixtures, which is k. So mu will be this. The variances will be k to 2k, and the pi's will be 2k to the end, right? So these are my parameters now. Okay, so for any mixture k, what is the f of xi that we computed? Pi k into Gaussian of mu k comma sigma k. Sigma of k is what? Square root of the variance. So mu k comma sigma k comma the data point. Data point is what? X of I. Okay, so this is what this is for the kth mixture. Pi k, the probability that we choose mixture k, and then the density of the point belonging to that mixture. Now, if I sum this, let me know if you understand this. If I sum this, what do you think I will get? And just go back to the formula quickly. You see what here is the denominator, right?
Yes.
That is what we have done. Pi instead of L, I have used k itself. Pi k into Gaussian. Pi k into Gaussian. Remember that, and we have summed it up. So this is what we are getting. Okay, so now this is the denominator. Denominator in the base rule, what is it called? Prior, posterior, likelihood. The context of base rule, what is the denominator called?
Likelihood.
Is it likelihood?
Evidence. Yes.
It's
Evidence.
called evidence, right? So it's called the evidence. So this is the evidence. What we have computed is the evidence. What is the prior?
It is the pi.
Prior is pi, right? So pi of k is the prior. What is the likelihood going to be? For the kth mixture, what will be the likelihood?
f of zi xi belongs to zi equals to k.
Correct, right? So that is the Gaussian. That is the Gaussian, right? So this will be the likelihood. This is f of xi comma given zi equal to k, right? That is the likelihood. So posterior is what we are interested in. Posterior is what?
Likelihood multiplied by prior divided by evidence.
Likelihood multiplied by prior by evidence, right? So this is the posterior. What is our posterior? A posterior in this case is lambda of, so lambda is a bad term because already there. So this is what is called lambda ik. Lambda ik, sorry, I'm moving between tabs, but lambda ik is a matrix, right? Do you get it? Lambda is a matrix now, because if there are 100,000 points, or let's say there are 100 points, and there are 3 mixtures, then I need to store 300 values. Correct? I need to store 300 values because there are 300 values for lambdas. How am I going to store this? I'm going to store this in the form of a matrix with 100 rows and 3 columns. 1 row for each data point. In each row, you will have the values for the 3 mixtures. Okay, I hope you get this part because this translation is important. So this is the posterior. Okay, so now all that I need to do is, evidence is going to be common for all the data points. So I'm not going to trouble that. I'm going to loop through all data points now for I in range of n. N is what? N is nothing but number of data points. How do I get that? X dot shape of 0, right? That is the number of data points. So for all the data points, for each mixture, for k in range of capital K, find the prior, find the likelihood, find the posterior. Your posterior is the lambda ik value. Okay, only thing is missing is something. Lambda is not defined. So how will you define the lambdas? Understood so far. What should lambda be actually? What should be the shape of the matrix lambda?
3.
So 1,000, 100,000 multiplied by 3.
Correct, right? Correct. 100,000 multiplied by 3. So I'll create a something like this, right? N cross k. Basically what we are saying. Rows are number of data points, n data points, k columns. So lambda will be of shape n cross k. For each of the data points, for each mixture, find the prior likelihood, then compute posterior. And lambda ik is nothing but the posterior. Okay, so that is what we have done. That's the E step. Use the thetas to get the lambdas. Use the thetas to get the lambdas. So how do we get the lambdas? We return lambda. Okay, so if you run E step on theta naught, let's say we started off with some initial theta naught, right? So started off with a theta naught here. So let me write it down. Theta naught is equal to init of, and we have some x that we already generated from our GMM, which is here. Okay, so if I initialize theta naught like this, and if I run my E step on this, I am getting an error. What is the error? Slice k somehow is giving me a wrong value. Okay, let me see. K here. Okay, I guess it should be int and not What is that? What it's saying? Are you all lost or are you all still following?
Following, sir.
Okay. Okay, so this should be an integer. That's the problem. Now next error is coming up here. Free variable I referenced before assignment. Okay, that's fair enough. You have to compute the evidence, right? So evidence should be where? For each data point, you need the evidence, right? So it should be inside. Y of k, then. So what is the evidence? Let's take a minute to understand the evidence. So for a given point, it's the density of the point, right? In the GMM. So do you get why the evidence should be inside this loop? This is f of xi, basically. What I call by evidence is f of xi. F of xi is what? Pi k into sigma pi k into f of xi given zi equal to k. In case this is not clear, please go back to this and see this. I am computing the evidence once for each data point. Okay, if I write it down, for a given data point, the denominator is fixed. Only the numerator changes from mixture to mixture. You get that? So denominator is fixed. It's a summation over all mixtures. But the numerator will keep changing from one mixture to the other. So for one data point, you need to compute the evidence once. And then you have to enter the inner loop and start computing the mixture-wise probabilities. Okay, so now let us run this and see. Okay, so some step we have some set of lambda. Let me call this lambda 1. Okay, so I think that worked. Now let's go back to M step. Now M step is the next part. Now we need to figure this out. Let me quickly write it down. So what is the M step going to be? Given lambda, estimate the parameters. So mean for the kth mixture will be what in the M step? The weighted sum of all the data points, right? So I go from I equal to 1 to n lambda ki, say. Okay, so if you want to compute, so this is the M step. If you want to compute the mean of the kth cluster, then the mean is the weighted sum of all the data points. What is the weight? Someone tell me what the weight is.
Lambda.
Sum of
Okay, so what is the lambda in terms of words? What is the weight? Weight is the probability that I belongs to cluster K, right? That is what the weight is. So the weighted mean of all the points, but then what is the weight? It is the probability that I belongs to cluster K. So this is what we have done. Now, likewise, you can very simply change this to sigma K square. So a simple change of formula. Again, weighted mean of all the endpoints. But instead of mean, it's the variance. That's the only change. Finally, you have 5k. 5k is what? You just remove this xi and you say sum of probabilities of all endpoints belonging to cluster k divided by n. So just to understand this, if some of the points completely belong to one mixture, this will be 1, right? Say the third data point, lambda 3, 3, 1, lambda 3, 1. If it completely belongs to mixture 1, then that value is 1. So what is this then? It's the total number of points roughly, right, that belong to a particular mixture. Okay, is this clear what these three quantities are? This is the weighted mean, weighted variance, and probability of choosing the kth cluster. Okay, this is clear, right? What the lambda, the pi k is. Sum of probabilities in the numerator. By choosing cluster k, you go through all the data points, sum all their probabilities of belonging to this cluster divided by n. Okay, so I hope you understood that. So we'll do this. Okay, so how do we do the m step? Has anyone done the same step already? Okay, so let's go ahead. Okay, so do you see why lambda dot shape will be n cross k like this?
Yes, sir.
Okay, so there are n rows and k columns. So this is the shape. Now I need to define 3 values. This will be again, I'll start with zeros, np dot zeros of k, and the variances again np dot zeros of k, and for the pi's np dot zeros of k, and for the weighted part, right? So for each data point, I need to do what? I need to multiply it by lambda of k, correct? So it's not enough if I just loop through the data points. I also need to loop through the number of mixtures. Sorry, this is should be outside, right? So because we are trying to compute mu of k, right? So we are trying to compute weighted mean. If you are trying to compute weighted mean, then I'm trying to compute mu of k, right? So for mu of k, I go through each data point, multiply the data point with its weight. Okay. Now add these values. I start with some 0 value. I add these values. And finally, my mu of k will be what? This value divided by, what should I divide it by? Anyone?
Sum of lambda ik.
Correct, right? So then I need that also. So let me write it this way. Let me write it as numerator, denominator. So this is the numerator, which is the weighted sum. Sorry, weighted sum. Denominator is just the lambda ik sum, right? So lambda ik. So mu of k will be then numerator by denominator. Okay, so clearly I need to do this for variance also. So it's okay, let me just repeat. Not okay to repeat this part. So shall I kind of introduce you to some NumPy functions which will make this easier? I think I hope this code is now clear to you, how we computed the weighted mean, multiply each point with the lambda ik parameter. So if this is clear to you, then I'll just quickly introduce you to one NumPy function, which is, so you can replace the whole thing with lambda of column k. See, colon comma k is nothing but the kth column of lambda. Remember, lambda is an n by k matrix. So if I want just the kth column, I can just do this. Okay, so the kth column will have how many entries?
N entries.
N entries, right? So I need to multiply these n entries with x. Okay, this will do this element-wise multiplication. This is nothing but the weighted sum. This is the weighted sum. Okay, divided by lambda of the kth column dot sum. This is all mu k is. All the nested for loop that I wrote here is actually just this single line of code. Okay, so variance of k likewise is, I just need to subtract my mu k from each data point, square it. Okay, so x minus mu whole square into lambda. Again, I have to weight it with lambda, right? Okay, so this is what it is. Sum this divided by sum of all lambdas for that particular k. That is the variance. Phi of k is what? K dot sum divided by, what should I divide it by?
N.
Divided by n, right? So now I need only one loop now for k in range of capital K. If I do this, I can get rid of all the other things. Okay, so that is all. So now what we need to do, we need to return theta. So theta is what? Theta is just putting these three things together. There is a function called concatenate in NumPy, which concatenates or puts them side by side. I need to put these things side by side, and I need to return this theta. Okay, so there is some syntax error. What is that? It's x minus mu whole square. Okay, so that into lambda k. There was a bracket missing, I believe. Okay, so this is what the m step is. Use the lambdas to get hold of the thetas. Okay, so once you have m step, you just need to do the EM algorithm. So I'll go ahead and write the EM algorithm quickly. While termination, I'll tell you what termination is. First, perform the E step on x comma theta, that will give you a lambda. Then perform the m step on x comma lambda, that will again give you theta back. Okay, initialize theta, of course. So theta equal to init of, right? So while termination, keep doing this. Okay, so this is the EM algorithm in terms of code. Okay, so now let's quickly go ahead and see what the termination is. Given two vectors theta and theta t and theta t plus 1, we need to find the distance between these two. Okay, so that will be the one which will help us terminate the function. So I'll write a quick function called distance, which gives us theta t and theta. Okay, so I'll call them theta old and theta new. How do I do this? What is the distance between these two? How do I compute that? Anyone?
Lin Elg.
Okay, that is correct. And the norm, right? So this is nothing but the norm. Norm of, it is what the distance is, right? Norm of the difference between these two vectors. Okay, so that is done. So termination is what? While you remember what the termination was here, we said while the norm is greater than epsilon, keep running. That is exactly what you are going to do. While the distance is, we need two thetas, we'll come to that. Called one theta previous and theta is theta current, right? While this is greater than epsilon, and epsilon is 0. Let's say 0.1, keep running. Okay, so I need to keep running as long as this distance is greater than epsilon. So I need these two previous values. I need the previous value of theta and current value of theta. So for that, what I'll do is I'll just go back in time. I got one theta naught, right? I have one theta naught. I will use that as my theta previous. Okay, and I'll do one iteration before I enter the loop. So if I do e step with theta previous, I will get lambda, and if I use this lambda to do an m step, so x comma lambda, I will get my theta current, right? So this is this, write this down, one iteration before loop begins. Okay, so this is one iteration before the loop begins. Start with one theta, do one e step, do one m step. So I have one theta previous and one theta. Okay, is this clear to everyone? At least clear to those who are following?
Yes, sir.
Yes.
Okay, so there's one small catch here. So I need to update theta previous also. Okay, so this is, if I use the current value of theta, I will get the new theta. Okay, so this is correct, but I also need to make sure that I don't erase the old value of theta. So I need to do this multiple assignment here. What is this doing? This is my current value of theta that should now become theta previous, and the new value of theta that I compute here should go into theta. So I need to do this. It's important that I do this. Okay, so I'll also have one thing to compute the number of iterations. Now I've written the code correctly, then should work. Let's see. Okay, it will take some 1 or 2 minutes if there are no errors. So Reese is saying this is it's saying none type. So what is the problem? I didn't return. Okay, so it was returning none. So I have to return something. Okay, I've returned that. Now let's run it again. Okay, roughly, if all works fine, then we should get somewhere around 70 iterations to completely solve this particular instance. Okay, so the reason it's taking time is there are like 100,000 data points, so it is going to take this time. We have to wait for a few more, at least 1 more minute. So while it's running, let's quickly look at the last problem here, which is hard clustering. So let me take a quick example, and I think this is something we did last time, but just to give you an idea of what we are really saying. So if you have lambda for, let's say, 5 data points and 2 mixtures, right? Then your lambda will be a 5 cross 2 matrix, right? So n equal to 5, k equal to 2. So it will be something like this, and you want to do a hard clustering, meaning for each data point you want to find out which cluster it belongs to using the EM algorithm. Okay, so if your lambda value turns out to be something like this, so let's say the lambda values turn out to be, what are we saying? We are saying that the probability that the first data point belongs to cluster 1 is 0.7. The probability that the first data point belongs to cluster 2 is 0.3. Here, cluster and mixture, I'm using it interchangeably. So if I do a hard clustering, currently they are softly clustered, meaning there is 70% chance that data point 1 goes to mixture 1. Okay, there is 80% chance that the second data point goes to mixture 2. So when I do a hard clustering, what I say is I can do different ways of hard clustering. So one way of hard clustering is the cluster indicator for the ith data point will be given by argmax over argmax done over the mixtures lambda ik. Okay, what do we mean by that? For the ith data point, look at the probabilities across all mixtures. Choose that mixture which has the maximum probability. So in this case, if I do hard clustering, this is what it will look like. Okay, so let me change it to 5 rows and 1 column. So these are all Z values. So here, first point will go to mixture 1 because that has the maximum probability. Second point will go to mixture 2, third to mixture 2, fourth also to mixture 2, fifth to mixture 1. Okay, so this is an instance of hard clustering for 5 data points, 2 mixtures. Okay, this is one way of doing hard clustering. All right, so it's still running. I don't know why it's taking so much time, but let's just stick around for 1 more minute. If it doesn't work, then we'll call it a day. If not, anyway, you can know the number of iterations. Can't. Okay, so it finished running. So as I think you can see what's happened. It's taken around 71 iterations to converge. Converge meaning based on our condition, right? Distance greater less than 0.01, it will converge. Okay, so let us go ahead and look at what final theta values we got. Okay, so we got something like -305. Okay, remember that the first three are the means, right? -305. What are the, so I'll print the actual theta values and also the theta zero, sorry, actual theta values are what? Go back. Where did we have it? Yeah. So -405213. Remember this, -405213. So actual values are -405213 and 1/3, sorry, 0.3 is the pi of first mixture, 0.5, 0.2. This is the true values and this is our estimate that we got from EM algorithm. Right, now compare this. So -4, this is -3.94, pretty good. This is 0, this is 0.02. This is 5.004, this is 5. This is 2.06, this is 2. And then you have, this should be 1, this should be 3. This should be 0.3, this should be 0.5, and this should be 0.2. Right, so that is quite close. Right, so this is what EM algorithm really is all about. So note that we won't have access to the true thetas. We'll only have access to the data X. We have to run EM algorithm to estimate thetas. In this case, what we have done is we have just in the interest of verifying our algorithm, we have done this part where we also generate the data and fit the parameters. Okay, so I hope this is clear at least to some extent for those who are present. Problem 10 is nothing but, so these are the true parameters. See how close our estimates are there or to them, right? So it's just computation of norm. I'm leaving this as an exercise. I think we'll be able to do this. Last part, okay, with this we'll end. How do we do this hard clustering? As I showed you, across the rows, you have to find the maximum. You have to find the argmax. So the way to do it is, NumPy has a very neat function called argmax. So axis equal to 1, if you specify axis equal to 1, it will give you the argmax along the rows. Okay, and this is your Z value. Okay, so this will be the Z values. So we have been asked to plot 3 histograms, all those points which belong to cluster 0, all those points which belong to cluster 1, all those points which belong to cluster 2. How do we do this? Again, very quickly I will do this. So x0 is wherever Z equal to 0. Okay, remember Z double equal to 0 will return a true false array, right? It will return this array. Remember what will Z double equal to 0 do? It will return an array where of all those points which have been clustered to cluster 0. So all that I'm going to do is take hold of these points. Okay, NumPy allows you to do this kind of indexing and plot a histogram with color equal to, this should be red in its color. Let's see if it works. Hit all those which have been clustered to 1, make them blue, and then finally make them green. Okay, let's make the bins somewhere around 100 for each one. Now let's run it. Okay, there is no property called C, so I think it should be color, if I'm not wrong. Okay, let's suppress the output. Okay, so that is what we get, right? So we did a hard clustering based on the argmax along each axis, along the horizontal axis, and that ended up giving us these points to cluster 0, these to cluster 1, these to cluster 2. So this is how EM can be used as some sort of clustering, hard clustering algorithm also, right? There are some extras which you can do if you're interested. What happens if you change the size of the data set, initialization, so on and so forth. But yeah, that is EM. So any questions? Are you all able to follow at least some 50% of it?
Yes, sir.
Yes, sir.
Okay. All right. So yeah, thanks for sticking around, those of you, and thanks for answering once in a while. So that's all I had. I'll just stop the recording. Unfortunately, streaming. Yeah, sure. Unfortunately, streaming didn't work today, but the recording is there, so that will be shared later.